Hello everyone, welcome to this session on the matrix iteration method. In this section, we will use the technique which is widely used in various engineering disciplines to solve complex engineering problems involving eigenvalues and eigenvectors. I am Dr. C. Sendamarai, Associate Professor in the Mechanical Department at SVC. We delve into the fundamental concepts of matrix iteration method initially, and then I will give you some practical applications based upon the matrix iteration method so that we can able to determine natural frequency for multivariable multi-degree of freedom systems. In the realm of engineering and physics, understanding the natural frequencies are very much important and crucial. These frequencies at which a system tends to oscillate with greater amplitude are vital for designing the structures that can withstand vibrations, and we have to avoid the resonance. One such powerful technique to determine these frequencies is the matrix iteration method. This method operates under the assumption that the system's natural frequencies are distinct and well separated. There is a step-by-step procedure for this matrix iteration method. Let me see that. To begin, we need to make a initial guess for the mode shape, which is represented as a trial vector. This vector essentially describes the relative displacements of different parts of the system during the vibration. While any non-zero vector can be chosen, a judicial initial guess can often speed up the convergence of the method. Step 2, it is pre-multiply by the dynamic matrix. Next, we take our trial vector and multiply it by the dynamic matrix denoted as D. This matrix encapsulates the mass and stiffness properties of the system and plays a key role in determining its dynamic behavior. The result of this multiplication is a new vector that represents an improved estimate of the mode shape. Step 3. Normalize the resultant column vector. The vector obtained in the previous step is then normalized. This normalization involves scaling the vector so that its largest element or some other chosen normal one becomes equal to 1. This step is important for ensuring that the iteration process converges to a meaningful result and prevents the vector from growing indefinitely. Step 4 is repeating the step 2 and 3 until convergence. The core matrix iteration method lies in repeating the step 2 and 3. We take the normalized vector from the previous iteration and use it as the new trial vector. This vector is then pre-multiplied by the dynamic matrix and the result is normalized again. This iterative process continues until the successive normalized vectors converge. This convergence is achieved when the change between the normalized vector from one iteration to the next becomes sufficiently small enough, indicating that we have found a stable estimate of the mode shape and its corresponding natural frequencies. Let we see the step-by-step approach with mathematical formulation from next slide. We have previously discussed the matrix iteration method for finding natural frequencies. Now let's delve into the theoretical foundation behind this method by examining the beginning of its proof, which relates on the concept of expansion theorem. Imagine you have a complex structure like a bridge or an airplane wing. Engineers need to know how this structure will naturally vibrate its natural frequencies. These frequencies are important to avoid dangerous shaking or even failure. One way to figure this out is using a technique called matrix iteration method. This method works best when the structure has distinct natural vibration patterns that are quite different from each other. Think of it like a musical notes that are clearly separate. Here is how the method works. First, we make an initial guess about the shape of the structure will take when it vibrates at its lowest natural frequency, that is x1. It is a guess that is going to be the vector selected arbitrarily. This guess is like drawing a rough picture of the vibration. Next, we take this guess and perform a mathematical operation on it using the structural properties like using the mass and stiffness, that is the system properties. This is the second step. This operation is like applying a special filter to our initial picture that we guessed initially. Then we adjust the resulting shape so that its largest movement becomes a standardized size. This is like resizing our picture to fit a specific frame. So that is using with this CI, we are using the unknown numbers which is determined after the convergence is happened. We repeat the last two steps over and over again. Each time we perform the operation and adjustment, our picture of the vibration shape gets a little bit clearer and closer to the actual shape of the lowest natural vibration. Why does this work? Well, the mathematical operation we perform favors the lowest natural vibration pattern. So with each repetition, the influence of the other higher frequency vibrations gets smaller and smaller, and our guess gets closer and closer to the true lowest vibration pattern. How many times do we need to repeat this? It depends on how good our initial guess was. If our first guess was already somewhat close to the real shape, we won't need to repeat the process many times. One good thing about this method is that if we make small mistakes in our calculations along the way, it usually doesn't throw off the final result too much. The process tends to correct itself as we keep repeating the steps. However, there is one situation where this method might not work perfectly. If our initial guess happens to be exactly the shape of one of the higher frequency of vibrations, then the method might get stuck on that vibration instead of finding the lowest one. But usually we make a responsible initial guess. This isn't a problem. So matrix iteration method is a way to find the most fundamental way a structure vibrates by starting with a guess and repeatedly refining it until it settles on the true pattern. The expansion theorem states that any arbitrary vector, which in our case is represented by x, can be expressed as a linear combination of the system's mode-shaped vectors. These mode-shaped vectors are denoted as x1, this is a vector, x2 vector, xn of vector are fundamental to the system's vibration characteristics. So we begin by expressing our arbitrarily selected known vector x1 as a sum of these constant mode-shaped vectors, each multiplied by a unknown coefficients c of I. Mathematically, this is represented as x1 vector equal to c1 x1 vector, and it will come sum up till nth to the power of vector. Here, the mode shape vectors are constant vectors because they are inherent properties of the system itself, determined by its mass and stiffness distribution. So our goal is to determine the unknown constants. To proceed with the proof, the next step involves pre-multiplying the D dynamic matrix. This operation is crucial in the matrix iteration method. Performing this multiplication, we can get D, the dynamic matrix, multiplied with vector. Then everywhere we have to multiply D along the summation of this. Using the distributive property of matrix multiplication, we can rewrite the right side of the equation as D of x1 and left side of the equation as like this. So in this step, set the stage for further development of the proof, which will likely involve utilizing the relationship between dynamical matrix, mode shapes and mode vectors. We will continue to explore how this expansion forms the basis for iterative process we described earlier. Matrix iteration method is a step-by-step process. We know that is, it is used to find the fundamental way a structure vibrates. It begins with a simple action. First, you have to select a trial vector. Next, you pre-multiply it by the dynamic matrix. This is a mathematical operation using the structure's properties to refine your guess. Then, you normalize the resultant column vector. This means you adjust the size of the resulting shape to a standard scale. Finally, you repeat the pre-multiplication and normalization steps over and over again. You continue this repetition until the vibration shape you get in each step stops changing significantly. This point of stability is when the method has found the fundamental mode of vibration. After we have repeated the steps of the matrix iteration method many times and our vibration shape has stopped changing, we have essentially found the shape of the lowest natural frequency or lowest natural vibration. Now, to find the actual value of that lowest natural frequency, we can look at how the vibration shape changed between two lost repetitions. Imagine you take a specific point on a structure and see how much it moved in the very last repetition of our process. Then you can compare that movement to how much the same point moved in the repetition just before it. This relationship calculation is to provide the value of the lowest natural frequency. It's like measuring how quickly the vibration pattern is settling down. The rate of settling is directly linked to the frequency itself. So, by comparing the converged vibration shapes with the one just before it, we can determine the numerical value of the fundamental natural frequency of our structure. The dynamical matrix has a special relationship with the system mode shapes and natural frequencies. When we repeatedly multiply by the dynamical matrix and normalize, we are essentially emphasizing the mode shape associated with the lowest natural frequency. Our several iterations, the contributions from the other mode shapes diminish and our vector converges to the fundamental mode shape. Finding the natural frequency omega 1, once the normalized vectors converge, we can determine the lowest natural frequency, often denoted as omega 1. If we look at the relationship between a trial vector in one iteration and the vector obtained after multiplying it by the dynamic matrix, after normalization in the next step becomes approximately proportional in the next step, becomes iteration of r plus 1. The ratio of corresponding elements in successive vectors given as an approximation of the square of the lowest natural frequency, that is omega 1 square, specifically for any element I in the vectors, will be approximately equal to omega 1 square. Here, main important points to discuss are number of iterations. Finite number of iterations is usually enough to get good estimate of omega n. The exact number depends on how close the initial trial vector is to the actual first mode shape. Next, computational errors. One advantage of this method is that small computational errors that might occur during the iterations generally don't lead to incorrect final results. The iterative process tends to correct these errors. The limitation is the method might be failed if the initial trial vector happens to be exactly proportional to one of the higher mode shapes, not the first one. In practice, this is often avoided by choosing an initial vector. Hence, the matrix iteration method provides a practical way to estimate the fundamental natural frequency and mode shapes of a system through a relatively straightforward iterative process. Let me see some examples and problems from the next slide. Now that we discussed the theory and procedure of the matrix iteration method, let's look at a practical example to see how it is applied. This slide presents a classical problem in vibration analysis, that is, finding the natural frequencies and mode shapes of a 3 degree of freedom system. Imagine we have three masses labeled M1, M2, M3 connected by springs. The first mass M1 is attached to a fixed point by a spring with stiffness K1. Mass M1 is also connected to mass M2 by a spring with stiffness K2. Finally, mass M2 is connected to mass M3 by a spring with stiffness K3. We can visualize these masses moving vertically with the displacement denoted as x1 of t, x2 of t, x3 of t. In this specific example, we are given that all the spring constants are equal, that is K1 equal to K2 equal to K3 equal to K. Similarly, the masses M1, M2, M3 all are equal to the value of M. Our goal is to use the matrix iteration method to determine the natural frequencies at which this system will tend to vibrate and the corresponding mode shapes which describe the relative motion of these three masses at each of these frequencies. The following slides will likely walk us through the steps of applying the matrix iteration method to this specific 3 degree of freedom system. This example will provide a concrete illustration of how the abstract concepts of the matrix iteration method are used to solve real-world engineering problems involving vibrations. Now, that we defined our 3-mass spring system. Next step in using the matrix iteration method is to formulate the system's property in matrix form. Here, first we have the flexibility matrix A. This matrix essentially tells us how much each mass will displace when a unit force is applied to each of the masses. Our specific system with 3 masses and given 3 spring constants, the flexibility matrix is derived to be 3 by 3 matrix with elements involving the inverse of the spring constant K. Next, we need the dynamic matrix. The dynamic matrix, often denoted as D, it is crucial for the matrix iteration method. It is obtained by multiplying the mass matrix of the system with the flexibility matrix. Here we are multiplying and getting the D matrix, which has been shown here. Notice it also a 3 by 3 matrix with elements involving the mass and the spring constant K. Finally, we are going to solve this eigenvalue problem by finding the core natural frequencies and mode shapes lies in this. Here D matrix represent dynamic matrix and we are looking for vector x, which will be our mode shapes, and scalar values, that is lambda. Lambda, which is related to the natural frequency, that is lambda equal to omega, we can take it as the value of k by m into 1 by omega square. So by finding the eigenvalues lambda, we can then calculate the natural frequencies of the system. Okay, here is a very important next step. We are going to start by iteration method. Now let's apply the first step of the matrix iteration method to our 3 mass spring system. Recall that we need to start with an initial guess for the mode shape, our trial vector. Hence, we are assuming a simple initial trial vector where the displacement of each mass is equal to 1. That is, mass 1 also displaced by 1, mass 2 also displaced by 1, mass 3 also displaced by 1. So our initial guess x1 is a column vector with elements 1, 1, 1. The next step is to multiply this trial vector with the dynamic matrix that we derived in the previous step. Performing this matrix multiplication results in a new vector. Looking at the slide, we can able to see that when the dynamic matrix multiplied with the initial vector, the resulting vector, what we are going to call it as, is x2. After commonly taking 3, we are getting the values of 1, 1.667 and 2. So the next part of the iteration involves normalizing this resulting vector. The normalization process by making the first element is equal to 1. To do this, we divide each element by 3. That only we are taking it here. That is taking 3 commonly outside instances, dividing everywhere by 3, 3. To do this and getting the value, that is the normalized vector is approximately equal to 1, 1.667 and 2. Finally, the approximate value of lambda 1, which is the eigenvalue associated with this iteration, is approximately 3. Using the relationship lambda equal to k by m into 1 by omega square, what we discussed in the last slide, we can approximately calculate the value of the first natural frequency as 0.5773 times of root of k by m If we know the k value and m value for the given system, we can able to calculate the natural frequency. This slide illustrates the first iteration of the matrix iteration method. We started with this initial guess, that is initial vector is x1 equal to 1 1 1. Afterwards we got a normalized vector, and here afterwards we are continuing with this normalized vector for the next set of iteration. After performing the first iteration, as we saw in the previous slide, we need to continue this process to get a more accurate result for the first natural frequency itself and mode shape. It is been stated in the matrix iteration method, we have to obtain the next trial eigenvector denoted as x with the subscript I plus 1 by simply multiplying the current trial eigenvector denoted as x with a subscript I with the dynamic matrix D. This is the core iterative step. We are repeatedly applying the transformation defined by the dynamic matrix to our current estimate of the mode shapes. Furthermore, this slide gives us a way to estimate the corresponding eigenvalue. It says that the eigenvalue can be approximated by looking at the first component of the vector, that is x with I plus 1 before it is normalized. So in each iteration, after we multiply with the dynamic matrix, first element of the resulting vector gives us an approximation of the eigenvalue associated with the natural frequency what we are trying to find. Hence, these formulas provide a clear roadmap for continuing the matrix iteration method. We take the normalized vector from the previous step, multiply it by the dynamic matrix to get a new vector, and then we can use the first component of this new vector before normalization as an estimate for the eigenvalue. We then normalize this new vector and repeat the process until our eigenvalue and eigenvector estimates are converge. In this slide, I am summarizing the result of applying the matrix iteration method over several iterations to our 3-mass system. We can see how our initial guess for the first mode shape and the estimated natural frequency gradually converge to a stable condition. Let's look at this table. The first column indicates the iteration number 1, 2, 3, 4, 5, 6 to 8. Second column shows the normalized trial vector at the beginning of that iteration, where the first element has been set to 1, 1, 1. The third column shows the result of multiplying this trial vector by the dynamic matrix. The fourth column gives the estimated eigenvalue lambda 1 obtained by the first component of the vector in the third column before the normalization. Finally, the last column shows the calculated natural frequency based on these eigenvalues. In the first iteration, starting with an initial guess of 1, 1, 1, we obtained an eigenvalue of 3 and a natural frequency of 0.5773 times the square root of k by m. As we move to the second iteration, our normalized trial eigenvector has changed to 1, 1.667, 2, and the estimated eigenvalue has become 4.667, leading to a natural frequency of 0.4629 times the square root of k by m. We can see a trend as we continue to the third iteration. The normalized eigenvector is now 1, 1.7857, 2.2143, and the eigenvalue is 5 with a corresponding natural frequency of 0.4472 times the square root of k by m. Notice that as we progress through a natural frequency through the iteration, the values in the eigenvector and estimated natural frequencies are changing less and less. And when we are going to the result for the 7th and 8th iterations, by the 8th iteration, the normalized trial vector value is 5.04892, resulting in a natural frequency of 0.44504 times the square root of k by m. This indicates that the mode shape and natural frequency converged in 8th iteration. This means after 8 iterations, changes in the eigenvector and natural frequency becomes negligible, and we have a good approximation of the first natural frequency and its corresponding mode shape for this 3 mass spring system. I conclude that here this table demonstrates the iterative nature of the matrix iteration method and how it converges to a solution for the fundamental natural frequency and mode shape after a certain number of iterations. Now that we have found the first natural frequency and its mode shape, we can use the deflation technique to be discussed and to find the second natural frequency of our 3 mass spring systems. This slide shows the initial step for this process. First, we see the formula for deflated matrix denoted as D2. It is calculated by subtracting a specific term from the original dynamic matrix. This term involves the first eigenvalue, the first mode shape and its transpose, and the mass matrix. This subtraction effectively removes the influence of the first mode from our system. Next, the normalized first mode shape vector, which was obtained from the convergence of the matrix iteration method in the previous step. However, it is noted that this vector needs to be further normalized with respect to the mass matrix. This is represented by introducing a scaling factor alpha. So the first mode shape is written as alpha multiplied by the vector 1, 1.8, 2.24, and then we explaining that how to find the value of this scaling factor alpha. It's seeing that the first mode shape, when normalized with respect to the mass matrix, should satisfy the specific condition, that is x transpose m x1 equal to 1. This means that we take the transpose of the first mode shape, multiply by the mass matrix, and then multiply by the first mode shape again. The outcome should be equal to 1. The calculation then shows the substitute the expression for the first mode shape, including the alpha, and the mass matrix, which is the diagonal matrix. After performing the matrix multiplications, we arrive at an equation, that is alpha square times the m multiplied by approximation value 9.29, which is then equal to 1. This equation allows us to solve for the value of alpha, which will give us the normalized first mode shape with respect to the mass matrix. Here in this slide, I am concluding that we seen that deflation process. We have defined the deflated matrix and are in the process of correctly normalizing the first mode shape with respect to the mass matrix, which is very crucial before we can proceed with the matrix iteration method using the deflated matrix to find the natural frequency of second mode shape. Following the steps that we outlined in the previous slide, we now have the value for the scaling factor alpha. Alpha is approximately equal to 0.327 times the mass matrix to the power of minus of the normalized first mode shape vector with respect to the mass matrix. It is approximately this one, that is 0.327, 0.59, 0.736. With this normalized first mode shape and first eigenvalue, that is 5.04892, from our earlier iteration that we concluded in the table 1. We now construct the deflated matrix D2. The formula for this we saw involves subtracting a term from the original dynamic matrix. So we start with the original dynamic matrix. It is represented here. Then we are going to subtract the term which is involving alpha, which is 5.04892, the normalized first mode shape vector, heat transpose, and the mass matrix. After performing this matrix multiplication and subtraction, we obtain the deflated matrix D2, which is shown here. This new matrix now represents the system with the influence of the first mode of the vibration removed completely. We now apply the standard matrix iteration method to this deflated matrix to find the next natural frequency and its corresponding mode shape. So I am concluding for this slide, that is, this slide demonstrates the crucial step of constructing the deflated matrix by removing the effect of the first mode. Now we proceed to identify the second natural frequency. Now we have our deflated matrix D2. We can apply standard matrix iteration method to find the second natural frequency and its corresponding mode shape. Just like when we are finding the first natural frequency, we start by selecting an initial trial vector for this iteration. Also, we are going to guess simply the displacement of each mass is again equal to 1. So our initial trial vector for the second iteration also 1, 1, 1 only. The next step is to multiply this trial vector by the deflated matrix, what we calculated in the previous slide. Performing this matrix multiplication results in a new vector that is labeled as x2. Looking at this, that we got x2. Finally, if we normalizing by removing 0.25763, commonly taking outside from this matrix, that means dividing 0.25763 for all values. We are commonly taking the value 0.25763 outside. So the lambda value is approximately 0.25763. So using the lambda and this relationship, we can able to calculate natural frequency, that is our second eigenvalue, and this is our second eigenvector. We would now continue to iterate this process with the deflated matrix using our table method until convergence to find more accurate value for the second natural frequency and its mode shape. Following the deflation process, we now apply the matrix iteration method to the deflated matrix D2. Here we are going to see how to find the second natural frequency using the iterations. Similar to how we find the first natural frequency, we start with the initial vector and iteratively multiply it by deflated matrix and normalizing it. In the first iteration with the deflated matrix, starting with the trial vector, we are all having the element equal to 1. We obtained an eigenvalue estimate 0.25763, which corresponds to second natural frequency of about 1.97016 times the square root of k by m. After the second iteration, the normalized eigenvector has changed and the eigenvalue estimate has become approximately 0.60032, leading to a second natural frequency of about 1.29 times the square root of k by m. As we continue our iteration, we can see the values converging. The slide here shows the result for the 10th and 11th iterations. By the 11th iteration, the normalist trial vector is approximately same as that of the 10th iteration, and the eigenvalue is approximately equivalent to 0.64300 in the previous one, and in the 11th iteration it is 0.64307, and the corresponding value of the natural frequency, that is second natural frequency, is approximately 1.2470 times the square root of k by m. Hence, there is a minimal change in the values at the fourth digit. We are going to stop the iteration at this point, and we are taking the value of natural frequency, second natural frequency, as 1.24701 and the vector as 1.4496 and minus 80192. I am concluding in this slide, that is, by using the deflation technique and then applying the matrix iteration method again, we successfully completed finding the natural frequency and its corresponding mode shape values. Having completing the first and second natural frequencies, it is our turn to find the third and natural frequencies, successive ones, for our 3 mass spring system. Since it is 3 mass spring system, we have to complete the third natural frequency, but it is an iterative process of similar fashion. We will use a similar deflation procedure as we did to the second natural frequency, so we can just compute the third deflated matrix. We need to prepare the second mode shape that we found in the previous step. So we have to normalize this result which we got as the second vector mode shape. This normalized second mode shape vector will then be used to find the second eigenvalue, and using the deflated matrix as usual, we have to use the mass matrix so that we can able to calculate the third natural frequency and its corresponding mode shape using standard matrix iteration method. Here I am going to stop with this because it goes on repetitive in nature in the similar way as we done it in the first mode and third mode. So by conclusion, we can able to solve natural frequency of complex systems by using matrix iteration method such a way to get accurate value for natural frequency and its corresponding mode shapes. We have reached the end of our session today. Let's take a moment to summarize what we discussed. As in this video, we started by introducing the fundamental concept of the matrix iteration method. Following that, a proof of how this matrix iteration method, a powerful iteration technique, was used by deflation matrix and expansion process. And the next one, by using a 3 mass system, a perfect example to find the natural frequency and mode shapes using this iterative process was explained to you very clearly. Thank you for taking the time to join me for this session.